ISR. Jal Janakal is the flagship project of this university. We are developing a hydrogen powered fuel cell based train. This train will not use electricity or diesel. It consumes only hydrogen. At SR University, we provide the students research-based learning for knowledge creation and innovative ideas. Further, we train the students with a desire to do and with a desire to learn and enable them to take up challenging tasks that they encounter in their career. We do recognize that the students' knowledge base must be sufficiently flexible to cope up with the 21st century job scenario. I understand that the conference has brought leading experts the areas of algebraic geometry and commutative algebra and young faculty members and research scholars. I'm sure that the conference provides opportunity for expansion of knowledge and awareness about current research problems in the areas of algebraic geometry and commutative algebra. I'm also sure that the conference could serve as an appropriate and a good platform for establishing collaborations between the faculty members of SR University AP and the distinguished participants of the conference. I wish the conference a grand success. Jai Hind, Jai Bharat, and Jai Vigyan. Thank you very much.
Thank you very much, sir, for addressing our people participants. So since we noticed that we are out of time, so we have to start our main program. So thank you very much for joining us, and as well as I am also thanking our Vice Chancellor for joining us from the USA. So thank you, sir, for your time. So now we start our curriculum activities. Thank you, sir. Yeah. So I wanted to say a few things about practical information, so which I will inform you later because we don't have time. We have to start. So now today's our camera.
Yes.
Yes.
Right.
Full skin mode. Okay, okay.
this name.
Yeah. Welcome all. First half of this conference, elaborate and very big one, I should say. So even before inviting the before lower confidence and tension from the there, but I should even begin with. So not even more. So I invite Professor meeting next day with our colleague KFR, and he will speak on order decimal classification.
Thank you, Parmeshwar. And I share the sentiments which Parmu expressed of admiration for the kind of organization you people have done. You are all very young organizers. It's not easy to take a conference of this size. Also, I'm most impressed by the infrastructure and facilities. And I'm really happy that the next generation or the next generation is going to have such nice facilities to do their business. Okay. And thank you for inviting. Let's see. So this is a somewhat specialized subject, but I'll try to go slowly for about first 20 minutes. Inevitably, things get. Can you hear me? Like, you turn it so that. But the I know it's on. Am I standing in the right place for your camera?
Yeah, they're capturing.
No, this is what is more important than what my case. Yeah. Okay. All right. So I'll go slowly in the beginning and try to explain in general terms what is the problem and what is done. And then inevitably it gets a bit technical. So algebraic geometry is a very wide subject, and in this conference it will repeatedly happen that the topics become specialized. But always one should endeavor to have a first substantial portion accessible to the general algebraic geometry. Okay, so with that in mind, let's go. Now the page down. After making it full screen, I think. Remove the full screen. Yes, all right. So I'll begin by recalling in very vague terms, general terms, the concept of semi-static. There are objects in mathematics like bundles, varieties, various other things. You might have seen moduli spaces for all kinds of things. And the objects that are very well behaved for this purpose are the so-called semi-stable objects. This is a general philosophy. And depending upon the kind of object you have, there will be a different definition of things. But they are all of a kind, which finally enables the semi-stability of GIT to be used for making moduli spaces. So the different kinds of semi-stability, as far as bundles are concerned, they are there for things like vector bundles themselves, which is where it began, of coherent pure sheaves, connections, principal bundles with a reductive structure group. A reductive group is something that we will talk about a lot. It is like GLN, SLN, classical groups, and some exceptional groups, their products, Tori. Nice things are usually reductive. And if you know GLN and SLN, you can always hear the word GLN or SLN whenever I say reductive. So these semi-stable objects, the bundles which are semi-stable, are better behaved in many ways. The remaining ones are called unstable. They are inconvenient, so you call them bad. You give them some bad name like unstable, okay, making them sound like crazy. And so you are justified ignoring them. So the remaining ones are unstable, and the semi-stable allow you to do many things, such as the Nussbaum Sexuality theorem, which connects the semi-stable objects of the bundle kind at least with representations of fundamental group and other associated groups. These objects are quote unquote bounded in algebraic geometry. There are not too many of them. They form finite dimensional families. And they lead to good moduli spaces, and many other nice properties are there for semi-stable. One of the properties is semi-stability is an open condition in any algebraic family. So almost everything is semi-stable. So not too many things are unstable. In terms of major theory, the unstable ones are major zero. So if you throw out the unstable, then it's okay. However, they are, because when you want to think of all the objects, there are certain nice formulas. And then you want certain nice, those kinds of nice formulas for the semi-stable ones, and for that you have to subtract the contribution of the unstable ones. So you have to understand the unstable ones. You cannot forever ignore the unstable ones. You preferably want them all together with a precise understanding of how much unstable. So Harder and Narasimhan began in the determination of the topology of the moduli space of semi-stable bundles by using Weyl conjectures, which had been proved by the recently. They quantified the amount of stability of an unstable bundle, and that is through the technology of Harder-Narasimhan filtration. For vector bundles, it means if a bundle is stable, it doesn't have some bundle whose degree upon rank is greater than the original bundle's degree upon rank. If it's unstable, there is one which has the biggest degree upon rank among all bundles, and go modulo that, and the next one again has, and so on. And this collection of subbundles, which contradicts the same stability in the most powerful way, is the Harder-Narasimhan filtration for that. So this philosophy of making the Harder-Narasimhan filtration for unstable objects would be implemented for all kinds of bundle-like things. So it can be done for parabolic bundles, or it can be done for X bundles, it can be done for principal bundles, which Ramnathan did, and so on. So you can have this kind of understanding of the unstable objects in terms of quote unquote filtration by semi-stable objects for a wide variety of bundles. So what does filtration mean? We'll have to make a bit more precise. So now, I'll change my. All right. So now let's look at families of bundles. After all, you want moduli, you want to know how bundles vary. So how does this instability change? So first of all, how do you characterize a bundle? By its discrete invariance. Before you talk of continuous invariance, there are discrete invariants. A bundle has its rank. If it's on a curve, it has its degree. It has its topological Chern classes. If you are working on a predictive variety, then you can calculate with respect to the ample line bundle, you can calculate its Hilbert polynomial coefficients of that, of the whole polynomial itself. These are like discrete invariants. So it has all these discrete invariants. And so we will talk of families of bundles. To begin with, we have to talk of a single bundle, and where will that single bundle be? That single bundle is not over your starting field. You can't restrict yourself to your starting field. You have to take an extension, and your starting bundle is on that extension. Because if you have a family of such bundles parameterized by some scheme, and you specialize it somewhere, there the residue field may be an extension of this. So when you want to think of moduli and semi-stability, etc., even if you begin with an algebraically closed field, you have to go to other fields. And you have to worry about what happens under field extensions because you are going to pull back the family. So will semi-stable remain semi-stable under extension of field? Such questions become important. Okay, so if one begins with a variety over a field K, which is larger than your base field B, you can attach to it a discrete invariant called its Harder-Narasimhan type, which is made from that Harder-Narasimhan filtration. There are various bundles occurring in that Harder-Narasimhan filtration. their successive quotients. Those have their Chern-Cassez degrees, Hilbert polynomials used as discrete invariants and call that as the Harder-Nussbaum type. So it's a combinatorial invariant you are attaching to anything which is unstable. When you attach this such an invariant, you find that these combinatorial invariants have an actual partial order. And in that natural partial order, the semi-stable ones are like minima. The number of different minimum points, because the topological types, the ranks are all different for different kinds of bundles. So if you fix one kind of starting topological data rank, then there will be a unique minimum, and that will correspond to the semi-stable objects. So now we are interested in how the Harder-Nussbaum type varies. So let's take a family. What does a family mean? First of all, there is a family of varieties. The variety also is not fixed, it can move. And there's a base space S, and on that your scheme X is over S, and the fibers are your varieties of interest. And the bundled or generalized kind of bundle is on X. So you take any point of this parameter space and you specialize there. Over that X has a fiber which is going to be defined. And I'll assume that these varieties really remain varieties on X. Means they are, so to say, geometrically or geometrically irreducible, and that this family is smooth. So all this based on this will also be smooth. Okay. And then there's a very ample, relatively very ample line bundle on X. So each one of these varieties comes to that. This is the concept of a family of varieties. The family of bundles is over this family of varieties. And now you want to know how their instability. So one can look at all those points of S where the restriction is semi-stable or its Harder-Nussbaum type is minimum. And that is an open system. And if you look at any other Harder-Nussbaum type, it is a combinatorial type of instability, then there is a certain locally closed subset where the type is that. Where the type is not greater than that or greater than equal to that, etc., are open, closed for their subsets, so that this Harder-Nussbaum type is upper semi-continuous. It's not constantly reduced. And so if you simply look at the topological type, scheme theory be damned, this was done in 1970s. They found out, Harder and Nussbaum found out this for the case of curves, and Schatz found it for more little coherent sheaves, that these topological properties hold, and you have topological stratification of the parameters. That used to be called Harder-Nussbaum stratification. Scheme theory, over in picture, just as the topological stratification. So I'll call it set theoretic. So now, personal history of my involvement with this. So my attention was drawn to this problem in my discussions with Camila Paz, and she was not scheme theoretic at all. But to me, I have to translate everything into scheme theory to understand what it is. And so I started asking questions of this kind: that is there a natural scheme theoretic structure on these strata, which makes them scheme with an appropriate universal property, not just locally closed subset. So what should be its functor of points? And is there an algebraic stack of a given Harder-Nussbaum type? One can also ask whether objects of a given Harder-Nussbaum type have modular space of some good properties. This question I won't go into this talk, but there are other people who are also at this stage. There is now some literature on it. Okay. So let me tell you about results. So my first question of this kind was about so-called coherent pure sheaves, which in particular includes vector bundles, torsion and whatnot. And for that, I proved all those properties. I showed there is a scheme structure, it has certain universal property, its functor is easy to describe, and they form an algebraic span. I think I could. I don't have to assume anything. First paper, it's mixed characteristics, smoothness not needed, almost nothing else. But that's for pure coherent. Okay. And then I began my collaboration with Sudarshan Pujar, who is there in the audience. When we started looking at these questions for principal. But first, in our first paper, we also proved that kind of results in mixed characteristic, no smoothness needed, nothing. For so-called lambda models. So it was fixed bundles, connections, logarithmic connections, what. But then we went on to look at principal G bundles or curves in characteristic 0. So while we looked at it, we developed various techniques, in particular palliative criteria, which we later found useful. But all that work, though it got us going, later it turned out that Behrendt had the similar result in his thesis, which we didn't know, and which to me even now is very difficult to believe. But anyway, so then we went on in characteristic 0 to arbitrary dimension. That was our second joint paper. And now we have our transcript on all characteristics, arbitrary characteristics, and in all higher dimensions. So this is going to be the focus of the rest of my talk, and this is joint work with Sudarshan. And therefore, if you have any difficult questions, I'll pass them on. All right, now. So let's talk of some basics of reductive groups. These are principal bundles. So as promised, I have spent about 20 minutes in very general terms. Yeah, 20. So you're on list. When did I begin? No, I began much later.
Yeah, you have something.
I am starting from 9:40. Right. 15 minutes I have done this. All right. So I have about 40 more. Great. So let's go slowly now. Okay. So here are some basics about reductive groups. One of my problems when I started looking at principal bundles was all my experience up to then was with algebraic geometry of the coherent sheaf kind, homology, coherent sheaves, blah, 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 and nothing about the theory of reductive groups. So I had to teach myself the needed stuff about reductive groups painfully while looking at this. But now, fortunately, I see there is a new book which very nicely covers everything that Stein needs. And that book is by J.S. Mill. No, he has not paid me to advertise this book. I'm doing it by myself. So this book I heartily recommend to anybody, especially the young people who want to learn the basics of algebraic groups in a modern way. Because the older books by Borel and whatnot are to me ununderstandable because I do not understand algebraic geometry as it was before 1965. Okay. If I have to understand algebraic geometry, please write it the way Grothendieck can understand. And anything before that is PC for me. So, all right. So this book is in modern enough terms, I can understand it. And very nice. Except it is this thing. That matter it is. Okay, so let me introduce a few terms from it. There's something called a split torus. A split torus is the algebraic group C star, if you are looking over complex. Yeah. K star. Okay. But now we are working on non-algebraically closed fields as well. So you better call it spec of T inverse. Okay. So this is a scheme, the group scheme, which corresponds to punctured affine. That's called a split torus of dimension 1. This product with itself is a split torus. And a torus more generally is an algebraic group which on base change becomes that. So for example, look at SO2R. SO2R, if you change it to SO2C, will become nice split. So here it's not split. Okay. Now a connected reduced linear algebraic group has to be connected and reduced is called reductive. All its connected closed reduced normal sources of group are chloride. Then you say it's reductive. You try it out on GLN with Sexuality. And with some simple linear algebra, you'll be able to verify all kinds of properties I want out reductive groups. You keep GLN in mind and do linear algebra and you'll get that. Nothing more than linear algebra is needed for most of the properties that I need if you specialize the case of GLN or SL. So these groups are all reductive, and a split reductive group is a pair where there's a group and there's a maximal torus, and that maximal torus happens to be reductive. Sorry, it is split. Such a thing is a split reductive. And then one can always choose a Borel subgroup, which in GLN terms you can choose the split torus to be the diagonal. And each diagonal is non-zero, so it's like star cross star cross. And the Borel is going to be all upper triangular and diagonal and upper triangular. Lower triangular entries. That's Borel that contains the torus. So such information we have to fix. In fact, we have to fix much more. So this is the kind of stuff I have to fix. This may look a lot if you are looking at it for the first time, but almost every lecture on a subject which involves reductive groups begins by a page. And so next time without reading, you know what. And the notation is also the same or with minor. So we'll have reductive group over the field K. I emphasize the word reductive group scheme because it's a scheme. It's valued points from a group. It's not a ring. It has a generic point. You can't multiply 2 points of this. You can only multiply values. And we are fixing a split maximal torus, Borel, etc. Okay. And then there are the corresponding simple roots. So what are these simple roots? So there is this adjoint action of G on its algebra, and the torus acts in a diagonalizable manner. And so the Lie algebra splits as a direct sum of its characteristic eigenspaces for different characters. And those characters are called roots. So there is a set of roots. And once you choose a Borel subgroup, the roots get split into positive roots and negative roots. And among positive roots, there are certain roots such that every positive root is just a positive combination of these. All this gets determined combinatorially once you choose your torus and Borel. So those are the simple roots. These are the corresponding dominant weights. There are certain weights of representations. Well, let me not go too much into it. We are referred back to L. And now there are subgroups called parabolic subgroups. I should say what's a parabolic subgroup. It's a kind of subgroup such that when you take a quotient by it, it's not normal. The Poset space G mod E has to be confined. So these are parabolic subgroups in complex analytic terms. It has a similar definition or in field. It's the quotient variety is complete. So there are so-called standard parabolics. Those are the parabolics which contain the Borel. Borel itself is parabolic, the full group is parabolic, anything in between is parabolic. These are the standard parabolics. And these are determined combinatorially because in this P, some of the roots get inverted, and the set of inverted simple roots is denoted by IP. From IP, you can go to P, from P, you can go to IP. To play a bit with linear algebra with the example of GLN to see how easy it is here. Parabolic groups have this kind of ladder-like shape. And so where exactly are you? It's a combinatorial thing. Now, what is the size of this block? This, and all the upper things are there and lower things are 0. It's a combinatorial manner. There are only finite given such choices, and those are exactly corresponding to the groups. And then there is a corresponding positive Weyl chamber, defined like this. You must have seen these pictures. Anyway, unfortunately, I cannot make this into a lesson on reductive groups. And this Weyl chamber as a partial order, all this is standard. And even if you don't remember all these details, you will be able to follow a lot of them. So let's look at principal bundles and semi-stability. I am assuming that all of you know what is vector bundle and semi-stability. When you have vector bundle and you have subbundle, now you can choose new transition functions which are in that block form, which take the subbundle into itself, and so the shape of the transition decreases as 0 in the lower left-hand corner. So that's exactly in a parabola. So your transition functions are now in a parabola. That's called a reduction of structure group to parabola. For principal bundles, we begin with that. Take a reduction of structure group to parabola. And then there is a condition for the subbundle having degree upon rank less or equal to the subbundle degree upon rank of the bundle. This is the semi-stability condition for bundles. So that you want to translate in terms of parabolic bundles. But now an added complication comes in, which you have to take into account. Once you work in higher dimensions, this reduction of structure group is not on all of your grids. Right? May not be. It's there at the generic point. And using evaluative criterion, you can expand this reduction to a largest open set where you can reduce the structure group. And that, by smoothness and evaluative criterion applied to the divisor, will contain the generic point of any divisor also. So what will remain is a closed subset of 4-dimension 2 or more. A tiny closed subset will remain. Rest of the place you will have this reduction of structure. So you have to formulate the definition of stability in terms of reductions to such large open sets. Therefore, big open sets. This condition that obviously 4-dimensional gets equal to known as big open sets. And then one might as well assume that your original bundle is also defined on something like this in order to define same stability, because this will be needed. And I must also mention that these bundles are supposed to be locally driven étale topology. They are not automatically locally driven. As you are well aware with examples of U2 bundles, Torus, that's a principal bundle with structure group. That one. These are skills for étale. This example was for étale local duality, not for connected. For orthogonal group, it will. So, as Suratmo was asking, what about a reductive group example? Because they're not good, being disconnected is not ready. So, think of orthogonal. Then you need square root of the experiment in order to make the what is known as Gram-Schmidt orthogonalization is what gives local duality for an orthogonal function. Gram-Schmidt involves taking square root. That requires you to go to an entire column. Assume that this cannot be the right one. Okay, so I have already gone through this. Reduction is also made, it's also done. And now we want an analog of this condition rank P upon PPT, rank PDPF minus rank FPT. And the reduction is only over a big open set. However, even on a big open set, things like degree make sense. Because degree is ultimately defined in terms of a line bundle. You take the determinant and that line bundle now extends to all of your variety projects. That line bundle is defined by divisor. You can simply take the closure of the divisor and use that closure to define your extension of your line bundle. And then take it. So the condition defining semi-stability works even if it's all happening on big open sets, and if there are no vector bundles but only principal bundles. This is the idea. This is a translation of that into relative group terms. Right? I have principal bundle on a big open set of a variety defined on an extension of your base field. I already explained why we need to go to extensions of these. And then I have rational reduction at the generic point. I have reduction to parabolic. It expands to a big open set. And of that, we have dominant character. That dominant character is going to produce a degree which corresponds to your rank degree E minus rank E. And so if I have any dominant character, this line bundle should have degree less than equal to this degree less than equal to 0. That corresponds to this. So here I explained what is meant by dominant character. But then you need to know also code. You will have to go back a bit. It's not particularly difficult. Anyway, for very large amount of mathematics, you need to know the basics of the theory of differentiations of, say, complex and simple groups and weights. So you have to learn this technology. Then all this is really very okay. So I said what is semi-stability. Now I want to attach a combinatorial invariant to the reduction. In order to define order-national type, I'll apply this combinatorial invariant to the worst possible reduction, which makes it shows up its stability in the most glaring way, the maximally destabilizing reduction of structure. So that I'll take the invariant that will be the order-national type. But in general, to any parabolic reduction, I should be able to attach a combinatorial type. So this is Ramanathan's thesis, and he defines it like this. Little bit of combinatorics. This type is going to be a virtual one parameter subgroup. X lower star T are all one parameter subgroups of your torus, and Q tensor with that, so you are also denominator. And then this Q tensored with characters splits like this. And because of this splitting, I can define an element of this dual space by telling how it acts on this part and how it acts on this part. And these two lines respectively tell you how it acts on this one, how it acts on that one. So this is how the type of a rational parabolic reduction is defined. And you see here it involves degrees of line bundles. Those line bundles are only on big open sets, but as I told you, a line bundle on a big open set, variety smooth can be uniquely expanded to a line bundle. So now let's say what is the canonical reduction or order-national interpretation analog for principal bundles. So it's a parabolic reduction such that, you see, you can't make it worse. Therefore, the very first subbundle itself has to be semi-stable. Otherwise, it will have some internal subbundle of even higher degree of moment. Right? So each of those graded pieces have themselves to be semi-stable. This is one condition. But the second condition, if you remember, is that you have chosen the first one to be worst, so its slope is highest. Next one has the lowest. Next one has the lowest. So there are two conditions. One is a semi-stability condition of that particular grade created, and the second is this inequality of slope. So these two conditions are respectively represented by the Levy quotient, which corresponds to the graded bundle. We have graded vector bundle from the order of computation, and each of the pieces is semi-stable. So the graded vector bundle has a graded bundle is semi-stable. Not semi-stable as a vector bundle, but it's graded. And that is the Levy reduction. Go modulo parabolic. Parabolic has a block form with 0 here. Levy means take those two blocks and 0 there also, there also. That's again a relative rule. The bundle corresponding to that should be semi-stable. That's one condition. And this slope decreasing condition gets translated into this. You have to stare at it some time and do the experiment with vector bundle to see, yes, this corresponds to what I know. Okay. So now, before going further, we will put a certain condition on our groups. You see, as I said, if one wants to talk of semi-stability and make moduli, one should have a functor. The functor should attach to any, say, parameter scheme, all families of bundles which are semi-stable. But then if I have base change, if it's a functor, the semi-stable should base change to semi-stable. Does it? For vector bundles, you can show it does. For principal bundles, why should a semi-stable vector principal bundle base change to a semi-stable? But fortunately, it does for a whole lot of groups, all the classical groups, even for the exceptional simple groups if the characteristic is large enough. And all this is also a consequence of something called Variant convention. I will briefly say what it is. And so we assume this property. Start with the assume that the group is such that if your original bundle is, the group is over this chota k, small k, original variety is over capital K, and now you have further extended to L, and the bundle is semi-stable on the original variety over X capital K, then it's changed to X capital L, is again semi-stable. So this we need for all dimensional varieties, but there is a semi-stable restriction theorem proved by Sudarshan, which shows us that it's enough to assume this for curves. Okay. All right. So this condition is satisfied by all classical reductive groups, and you can read more about this in Heinloth's paper. And what is this Variant condition? Let me quickly just give half a minute to Variant condition. See, Variant was the one who first proved that canonical reduction exists, the curve case. And he proved it is unique also in the curve case. But what he couldn't prove was whether it is infinitesimally unique. Can you infinitesimally vary? No, not actually. That he couldn't. So that was his conjecture, right? It turned out the conjecture is false, not everything. But it is true for most of the groups. And so, it's being infinitesimally unique is very important. Because that will also guarantee that the base change under a field extension of the semi-stable remains semi-stable. How? How do you show something remains the same on a base change? By applying Galois theory and trying to do descent. If there is uniqueness, then under any Galois symmetry, it will remain itself, and so it will descend. But if it's not separable, because it's purely inseparable, then the tensor product of the series itself is not going to be reduced. There is going to be infinitesimal motion possible in this tensor product. So you want infinitesimal uniqueness also. That will guarantee that it satisfies the Bernoulli flat descent condition and comes from. So that is the reason. Okay, I have not spoken on this subject with Variant. As I said, I find it difficult. But I imagine this may be one of the things that I find. Okay. So let's go on. So we'll assume this condition. So with this condition, Variant showed that given a principal bundle, there is a unique canonical reduction. It's tied with the hardness. This I believe we did over curves. And when you have this hardness type of the canonical reduction, because of the inequalities involved, the hardness type, that the first bundle has the greatest, then the next step has the greatest degree proportion and so on. Because of this positivity translates to the hardness type being in the closed positive range. And the smallest one maybe, well, here I said vertex 0 equal to, that is, well, I should have expanded to say that in the semi-simple case it is 0, then it could be something else also. I should correct this particular line to say this. And other people approached this. Polla and Biswas gave a proof in the paper, and Sudarshan and I gave another proof, which we believe is the most natural one. Because we go in terms of maximality of types in that, and we show that the one which is maximal is unique and it is the canonical. So we have, and apparently Ramanathan also knew this because he mentions it, but he never wrote a book. He died early, so now you can't ask what was this. All dimensions, and a very natural. Not that reference to the third paper. But okay. So let's go. So now we come to families. This is where our special problem begins. We want to do it for families. So far, whatever I told you, previous people did for instruments was over a single variety. And at the most, it's base change under a fixed. Now I have family of varieties. Or even if your variety is fixed, it will be even a constant family of varieties. But I have family of bundles more important. And I want to know how the type changes. And I want to know something more than simple. But anyway, we begin by proving all those semi-continuity Shax-like statements. Again, in our paper, high-speed topological semi-continuity is first of all proved. And then we give it an appropriate scheme structure and show there is an algebraic stack. We describe its functor of points. And we show what is the relation of this functor of points with the functor of points for all principal functions. What kind of morphisms are all this we study and algorithms. So let's see what it is. So our idea of defining a relative reduction is this. You see, here comes the difference between a single smooth variety and a family of smooth varieties. If I have a single smooth variety and a big open set and a line bundle on it, it has a unique prolongation to the full variety. How? Because this line bundle on that open set is defined by a divisor, by divisor. Take its closure and take the line bundle defined by it. That is fixed to the. And that's only one which can change. So on this big open set, there is this identity isomorphism. And so by coherence, it extends to a unique isomorphism. But if I have a family of varieties, this is no more. So we suspected. I was sure this is not. But Najmuddin showed me an example where it was indeed false. It's given in our second paper. Anyway, so even ahead of that example, we had the right definition, and the right definition is this, but that example shows that we were good to be so careful. So our definition of a family of principal bundles of a given Hardan type says that, okay, to begin with, you take this parabolic, take G mod P, which, as I said, is a positive variety. It has a very ample line model. That's an anti-canonical line model. If you have smooth variety, it has a standard model. Then it has a top exterior, the top exterior of the tangent. Omega is the top exterior of the cotangent model. That's why you see that inverse thing. Okay. That one is very ample. There's a name to varieties for which the anti-canonical bundle is very ample. What do they call? Yeah. Oh, no. So this is a Fano variety. And so it has a projective embedding given by this. This is a representation of G. Because on G mod P, G acts. But therefore it acts also on the tangent model. Therefore it acts on the top exterior. And so there is an action on the variety with the line model. Therefore there is an action on the H naught of that. And so this embedding, this projective embedding is G invariant. Now in this G mod P, there is a special point EP. You take the fiber only. P fixes that point EP. Therefore, P will act on that fiber of O minus 1, right? And that's a representation. That representation I am calling lambda. Using this representation lambda and the parabolic reduction of structure group, I make a line bundle on this big open set. And now I say that to be called a family of bundles of the given order type. This line bundle should belong to the entire. That is our definition from our second paper onwards. Third. In our first paper, we didn't have to worry because a big open subset of a curve is all of the curve. There is nothing in a, there's no closed substrate in a curve of 4 dimension 2 because curve has only 4 dimension 1. This problem didn't arise. But dimension 2 onwards, this problem came, and this is our answer to it. That assume that the line model extends. Once it extends by appropriate use of GA, that extension can be. So, whatever definition we make of a family, it should reduce to the old definitions in case the family is parameterized by a single field. And then it obviously does because on a smooth variety over a field, all that noise. You don't have to say more. So this is our definition of a relative reduction. It's only a rational reduction. There is a point and therefore over a field. This big open set will vary as you move your point in the family. So what one should call it is relatively big open set. Each fiber is big. So with this now we are going to define the groupoid of bundles of type tau. That's our announcement type bundles. So let's remember that we begin with a field, a split reductive group, is a chosen Borel, and we are going to assume the condition star. And now you take a family of smooth varieties of geometric reducible productive varieties on a Noetherian case in S. And then for any further base change, you look at the functor which associates to it, the family of principal G bundles of type tau. So we prove by working the machinery of faithfully flat descent that this is indeed an algebraic stack. This groupoid is an algebraic stack. So first of all, this groupoid is a stack. It's a sheaf in topology. And then it's second, it's isomorphisms are sheaves. It's all the descent is effective, there's descent is stack. Then to prove it's an algebraic stack, you have to show its diagonal is differentiable and it has an atlas. So we'll come to it as an atlas. So that involved as one. So we show that this is indeed star is satisfied, then this is an algebraic stack. There's this open substack, these open substacks, and G bundles on fibers. So there are certain open stacks, and then this is algebraic stack of type tau. And so, for any tau, this is a groupoid. Then this is an algebraic stack. The forgetful morphism is schematic of finite type, separated, radical, subjective, and induces an isomorphism on all its fields. And this forgetful morphism is finite, and if parent conjecture is true for your group, which means most of the groups you are interested in, there are exceptions, then it is in fact a closed. And so I am to my last slide, and I will make a few remarks on the. So as I said, a rational parabolic reduction will correspond to a certain line bundle. It will give rise to a line bundle. That line bundle belongs everywhere. And that line bundle has a certain morphism into this vector bundle made with the representation dp. dp was a representation on the H0 of the anti-canonical bundle of G1. So that line bundle has a which is injective, fiberwise injective on a big open set. So elsewhere also, as a sheaf theoretic map, it's not fiberwise injective, or it's clockwise. So you somehow need to classify to represent the functor when you have certain sheets somewhere up there on a family of varieties, and you have its right image, and you have another line bundle mapping to it, and injective at almost all points. Set. You need to be able to represent this functor of such maps. And that is the new technology we introduced in this paper so there is something well known called Grothendieck Q-sheaf. A Q-sheaf comes from Grothendieck's semicontinuity complex. You take the semicontinuity complex, take the first. So the semicontinuity complex consists of, if you were affine locally for a complex of positive non-negative complex of predictive models. Or if you want to talk geometry, some vector and maps. These maps are not of constant. You take the 0th to first map, take the transpose of that from the dual to dual, take its co-kernel, and that is the so-called Grothendieck Q-sheaf. This sheaf plays a very important part in all constructions, like Hilbert and Cope scheme and so on. Okay. So, idea was to take the proj of this. The spec of this has been there in literature for quite some time. That I discovered in my thesis, but later I found out that I didn't even know that this is called Q-sheaf. I found out by in our talk that the audience knew all about it because I was in the wrong city. And they said, "Oh, don't you know this is called Q-sheaf?" Oh, so, but you take the proj of it, and that represents this functor. And then once you have that functor, that goes into creating the atlas. And then the standard tools for dealing with coherent sheaves on projective schemes. This is like flat descent, semi-continuity, base change, flattening certification, Castle-Newton, Mumford regularity, Hilbert and Cope scheme, relative duality, homology vanishing of the, in this case, every heuristic kind, etc. See, more or less the entire gamut of techniques that all people working with coherent sheaves have to know, we have to deploy, and I had to run back to my EGA and open and here and there to implement it. So it was a good exercise. And then finally, with you have to combine it with basic facts of it. Then the theorem comes. So that is all that I have to tell. Sudarshan, you want to add any remarks? All right, so that is it. Thank you.
Any questions or comments? Go on, Balaji.
No, I didn't have any question. I just wanted to applaud.
Balaji, follow.
No questions right now. No, I was just thinking about all these things. It's all.
Yeah, I have a question. In between, you mentioned about that Galois descent.
Yeah,
And then you said something about uniqueness and tensor level.
yes.
But anyway, it's well known even for bundles that differ per star of bundles when not semi-stable, when not semi-stable. So what does this infinitesimal stability working on?
Infinitesimal stability means, or rather, see, if you have a canonical reduction, okay, take a canonical reduction.
It's like Harder-Nurseman.
Harder-Nurseman filtration. The Harder-Nurseman filtration should be the same,
But
unique even in principle.
But for any infinitesimal or only for group schemes, because f of star of bundle is not semi-stable. Right?
It depends on what it's. So this is if you have field extension, say an inseparable field extension, L over K.
Yeah.
Over L, you have a Harder-Nurseman filtration. Suppose it was not changed. So over L, there is a Harder-Nurseman. Okay. Suppose your starting bundle is semester, but suppose its extension to L is non-semester. Then it is Harder-Nurseman filtration. Okay. Now you go to L tensor L over K. And there are two ways of putting back.
Okay, the fiber product of extension.
Right. Suppose those two pullbacks will be the same. Then faithfully flat descent will show that the Harder-Nurseman flat will be the same.
But is it a group theory? You mentioned
No,
something.
this is not group theory. Now, so here for separable it was okay.
Yeah.
But now purely inseparable.
This is bundle.
When
Problem.
you work in positive characteristics, you have to deal with this also.
It's a purely bundle problem.
Yeah, it's a bundle algebraic jointing property. You see, nowadays they start using the word Galois theory even for purely inseparable.
Yeah.
There are a lot of, let's call it purely inseparable Galois. You want that to work. Okay.
No, but if it's actually like this Nori kind of a group scheme extension, though it's inseparable, there might be some extra. That's what I was wondering.
Hang on. This is about a field
Just
extension. And then if these two pullbacks are the same, then by Bernoulli flat descent, that thing was defined below. But then its degree, rank, etc. are the same below. So it will contradict semi-stability. So if some things pull up was non-semi-stable, then it must have been non-semi-stable. So provided there is this.
It's only provided, so it depends on.
Oh, yeah.
I had a question.
Which,
Balaji.
Balaji.
Yeah. So if you work in the absolute case and work with a high dimensional picture like projective surface,
Yeah,
and you can still, I mean, you can talk about this Bun tau stack.
Yes.
Isn't it, I mean, with the fixed polarization that we are working with, isn't it natural to ask if there is a restriction theorem for the stack itself? I mean, is it natural or is it, I mean,
This question I direct to Sudarshan, who is the one who had proved that semi-stable restriction theorem. Oh.
I don't want to make a statement presently.
But Balaji, I'll expect this will work.
I see.
Using whatever he has proved in the absolute case, moving to families should not be a problem.
Okay. But the restriction theorem is for the.
I tell you why I am confident of this. Our second paper deals with how to leverage restriction from a single variety to a family. So the technology needed for that is there.
This question is not about families, but for
No, in fact, I was actually
He
asking.
said whether it goes to stacks, so therefore he is talking of family. The variety may be single, but the family is 500. Yeah, so our second paper deals with how to go from how to handle semi-stable restriction in higher dimensions by going to hypersurfaces locally appropriately. So in fact, that second paper is very complicated. So it uses this technology. This third paper with this trick of proj of the Grothendieck Q sheaf just cuts through all that. And so the third paper gives a much easier proof of the second paper. But for the question you are asking, you have to use the technology of the second paper, and I would expect the answer. Yes.
Okay. Okay.
Any other questions? Yeah, Krishna.
Balaji, are you going to come here? I hope.
No, various apprehensions, and I will be only giving an online talk. Unfortunately, I would have liked to come.
Okay.
Still, there is this fear, and especially not having taken the third booster or whatever it is, it's all too much of fear in family circles.
Okay. All right. See you some other time.
Yeah, I would love to. Yeah. But I'm giving the talk on Friday. Yeah.
So thank you.
So, yeah. And maybe we'll just cut short our break to 6 minutes. Yeah, we'll come back at 10:45.
You're back in Hyderabad.
No, Balaji, I'm in Atlanta.
Okay.
Yeah, it's 1 p.m., 1 a.m.
Good. So they put me through, and I was in this Banff thing. It was like that for me.
Yeah.
Horror. Because I was attending another conference in Edinburgh at the same time. It used to end at 8 o'clock, and then this started at 8:45.
Okay.
So many times I skipped because I just couldn't even sit and keep my eyes open.
Yeah. So the many people are in person there is, yeah. Nitin went
Looks
there.
like it, yeah, looks like it. Yeah, I would have loved to go, but
Yeah,
suddenly
me
the number of cases increased here, and my wife was a little apprehensive because we have a daughter who has not been vaccinated. You know, she
Oh,
can't,
okay.
she's too young, and
Yeah.
that was, I think, the problem.
Right. No, I
That-
was
she's
in
very-
Hyderabad, yeah, till end of May. So I
Ah.
just came back. So
The children still don't have a vaccine, at least in India.
right, yeah. Here everyone is having vaccine. So I had the fourth booster, like fourth dose. It's the second booster.
Yeah, I know this is, it'll go to very large primes, it looks now.
Yeah. No, I think, yeah, it's like the flu vaccine here. Maybe one needs to take every year, probably.
Yeah, it's like the flu vaccine, right?
Yeah. So we flu shot we take every year, right?
I don't know what it does to the system, but anyway, we have to take it, I think, if you have to survive.
Yeah. So next is Jaya, right?
That's right. I saw her actually just now.
Oh, okay. She's also online.
Oh, offline. She's there.
Offline.
Physically there. I saw her there.
Oh, she's there physically. Oh, I thought you saw there means you saw in
Just
Chennai.
not here. She was standing here near the screen.
Oh, okay. I didn't see. Yeah.
It would have been nice to meet everybody and go there.
Yeah, it has been
For me,
long.
it's 5-6 hours journey from here to Vijayawada.
Right. By train or?
By train, yeah, there are very good car roads also now.
No, but the rains, I think it's difficult.
Yeah, that may be the problem. Yeah, that could be a problem.
The heavy rains, yeah, it's difficult to go by.
Train
Car.
would have been easiest.
Yeah.
So many trains are going. Any train which goes northwards.
Right. Yeah. Yeah. Yeah, I never been to this university also, so it's supposed to be nice.
You knew
The SRM, yeah, the new brand.
Kannan is the force behind it. Yeah,
Yeah, Kanan is behind this maths department there.
that's right. They put together a nice conference.
Yeah, it's very nice. So when are you coming this side?
There's a possibility early next year. I was thinking, let's see, but I mean, I don't have any. Some agenda, something was there. I mean, I was supposed to go to Berkeley with Constantine Telemann is there. And
Okay.
yeah, but it may happen only in 24, it looks now. Let's see how it goes.
24.
Things get planned very early these days,
Yeah.
including visits. Next year, yeah, but I'll come, I think, yeah.
Okay.
We haven't been to the US. It was in 2019, I was in the US. It was just before the COVID. In fact, we came back via Hong Kong. And it was completely empty, Hong Kong. And we could go to the Disneyland without any problem. But COVID was still there. It had just started in its big way.
Oh, so it's end of 2019.
That's right. We were just there in December and we didn't know anything. We were in the airport. We went from the airport to the Disneyland and came back here. And then this huge thing started in January.
Yeah, it's
Sexuality passed away in July of 2020. About 8 months after Sundari passed away.
Yeah. So how is Sridharan? Do you see him?
Yeah, I've seen recently. I mean, I talked to him about a week back.
Oh, okay.
Pretty weak and happy and unable to do anything, basically. He's confined to the house. He can't step out because various problems in his house. Yeah.
Yeah.
He has not come to the institute, and that's also, I mean, he used to get some change by coming to CMI.
Right, yeah.
But you needed Vasanta at home to handle all that.
Yeah, that's true.
Now she's not there, so he can't do anything.
Yeah. It's
A very sad situation. Raja has been there in Chennai.
Yeah, I know. Yeah.
Sabbatical 1 year. It's tough. Yeah. I saw him about a month ago.
Okay.
It's really difficult to talk to him because he's walking up and down the road to go and buy something and come back quickly to his home, I think.
Mhm.
He can't leave his daughter alone.
Yeah.
Too many tragedies in 2 years. Yeah. Anyway,
Yeah.
there's Jaya there now. I saw her.
Oh, yeah. Yes.
I disappeared from the visibility.
Yeah, she's there on the side, little bit you can see.
Right, I can see her. Yeah.
Just the arm.
They can hear our conversation, I think, right? All of them, unless they have muted us.
I don't know.
Hello, Jaya. Can you hear us?
No response.
Good.
Even section. Even section. One question.
So we're able to hear them, so but they're not able to hear us.
I think unless the question answer session comes, they don't open up at these schools.
Forget them. Oh, yeah.
Yeah, so welcome back to the second talk. And speaker is Professor Jaya Iyer from IMSC, and she will speak on regulations of canonical extension.
It is regulators.
Regulators, sorry.
Yeah. So firstly, I should thank the organizers, Sajad and Suranu, Ranjana, for organizing this wonderful meeting. And so also actually I'm very happy with Sajad. I remember teaching 10 years ago at Hyderabad University.
Can the volume be increased a little bit, please, if you don't mind? I'm not able to hear it.
Yeah, so is this better?
Much better. Fine. Thanks.
Yeah, so Sajad, I think I taught him, I think maybe around 10 years back, and I'm happy to see how he has blossomed. And I was sort of surprised when I saw this invitation, but then I saw the program and all, and I was glad to see that. Yeah. Okay, so yeah, so I would like to speak on regulators of canonical extensions. So this is some joint work with Carlos Simpson. So let me briefly tell you. Why is it not moving?
That's one. This one.
Right. So just to give an overview, so I would like to start with yeah, hello. This is better?
Yeah.
Okay. Yeah, so in this talk, actually, I would like to discuss certain invariants of vector bundles with additional structures. So as we know that actually when you start looking at vector bundles, which was essentially introduced by Mitsure just a few minutes ago, an hour ago. And so one likes to look at associate certain invariants to objects in algebraic geometry or even in differential geometry. And so starting with vector bundles, so one classically associated Chern classes. And now if the vector bundle is equipped with additional structures, so which we call as connections, so then one would like to associate invariants associated to such additional structures. And these invariants are topological invariants. Because when you are studying algebraic geometry, like you are looking at a smooth projective variety, or in differential geometry, you are going to look at smooth manifolds. But all these objects actually underlie a topological space, and the invariants are topological in the sense, what I mean by that is that whenever you start studying a topological space, so you like to attach certain invariants which classifies your topological structure. So that is precisely given by your homology groups or your cohomology groups. So these are sort of generalizations of your fundamental groups, which are the basic invariants you look at. So when your topological space is equipped with a smooth structure or a projective or an algebraic structure, so the invariants are still topological, I mean, at least to begin with. And so this is the content of this talk, that how do you associate topological invariants associated to additional structure on vector bundles. So the classical theory is due to Chern-Weil. So this is called the Chern-Weil theory. And then we are going to look at the connections, and we associate the primary classes. So these are the Chern classes. And now if you associate, look at connections on vector bundles, and you can further assume that your connection is flat. So I'll just explain during the talk what that means. So then you would associate what are called as secondary classes. So these are again cohomology classes in odd degree cohomology groups of your underlying smooth manifold. And now actually you can look at variation of flat connections. So variation is again something which was explained by Sure. So because you are going to look at, so he essentially said that, okay, you have a family of varieties. So something like, okay, now you have a variety is fixed, and then you have a vector bundle is fixed, but you can have a variation of connections. And then one can ask, okay, what is the invariant you would attach? So that is what I mean by one parameter variation of flat connections. And so all this study essentially converges to certain notion of cohomological invariants, which one can look at on the moduli space of flat connections. So this is something which I would like to explain. And so the next question is that suppose you have a X, which is a smooth projective variety, and then you fix a normal crossing device at D, and then you have a flat connection on the open part, X minus T. So there is a way to extend it across the boundary. So Mitsure did say, okay, how do you extend line bundles? But if you look at a D, which is actually in codimension 1, so there is not a single, no single extension. So there are several possibilities. And because you are, at least on the open part, you have a flat connection, it is possible to extend your vector bundle across D. And so this is what we would call as the canonical extension. And now we would like to look at invariants, topological invariants associated to the extended bundle with the extended connection. So which is no longer a flat connection, but a logarithmic flat connection. Okay, so then the last two part, the volume regulators and triviality and the Chern-Simons classes. So this is something I would like to explain next. Okay, to begin with, so you start with a vector bundle on a manifold. So which is the first vector bundle, natural vector bundle we come across. So this is something living on your Grassmannian. So you have the universal vector bundle living over a Grassmannian, and then you want to define certain invariants associated to the universal Grassmannian. So there is a way to define cohomology classes associated to the universal Grassmannian. So this is due to Whitney. And so what this also means is that what a theorem says is that now if you start with any smooth vector bundle on a smooth manifold M, so then there is a classifying map from M to an appropriate Grassmannian, so that the universal vector bundle pulls back to the given vector bundle you started with. So this also says that the Chern classes which live on the Grassmannian, so they can be pulled back along this map and correspond to what we call as the primary classes or the Chern classes of your vector bundle. Okay, so now the same theory. So at least what the first paragraph says is that corresponding to a vector bundle. So this is one definition to define the Chern classes of your vector bundle. So these are going to be some cohomology classes in the even degree of your underlying manifold M. Okay. Okay, so now actually if your vector bundle, a smooth vector bundle, is equipped with a connection. So what the connection means in loose terms. So this just means that it gives some formula to differentiate local vector valued functions on your manifold M. So because your vector bundle is going to be locally trivial, it looks like a product U cross CR. So any section you can think of it as a tuple of smooth functions. And then you want a formula which would say that how do you differentiate a tuple of smooth functions simultaneously. So that is some formula and which one can call as a connection. So starting with such a connection, so the classical Chern-Weil theory says that you can define the Chern classes corresponding to this connection, and this is with respect to the connection. So because earlier what we said that corresponding to a vector bundle, you are able to define the primary classes, and corresponding to a connection, you define classes, and this is actually the Theorem cohomology of the underlying manifold, and this is given by the trace of the connection form, taking the powers of your connection form, curvature form theta, and so that corresponds to again classes in the even degree cohomology of your manifold, but with complex coefficients. So you can also, if you are going to look at real value differential forms, so you would actually get the invariance in the even degree cohomology, Theorem cohomology with real coefficients. But actually it's not so bad, because the Theorem's isomorphism theorem says that the topological Chern classes, which is defined by pullback of your classes coming from a Grassmannian. So this is identified with the classes defined using the differential forms. So via the Theorem isomorphism. So this is either with real coefficients or with complex coefficients. Okay, so now next we look at the situation when your connection is flat. So flat essentially means that the curvature form is, so this is just taking the connection if you denote by say nabla. So this is going to be nabla composed with nabla. So that is the curvature form theta. And then we say that the connection is flat if the curvature form is identically trivial. So actually there is a nicer way to understand a flat connection. This is basically saying that whenever you are, because once you are given a vector bundle, so the basic technology is that there should be transition maps, so that locally you know that it is trivial, and on the overlap, so there are transition maps which takes values in say GLN or SLN, whatever. And so essentially, if those GLN, the transition matrices, if they are given, their entries are constant, so then one knows that your vector bundle is equipped with a flat connection. Okay, so in some sense, you can say that your flat connections is almost trivial, because we are just saying that the transition maps are given by constant values, and so it is almost trivial. In that sense, one can say that the topological classes or topological invariants you attach, so they are also going to be almost trivial. Okay, so let us make that precise. So because as I said that your Chern-Weil theory says that the cohomology classes CIE nabla with respect to nabla. So this is written in terms of your curvature form. And so if the curvature form is trivial, then these classes are trivial. So, okay, so now the question is that, okay, once you are given a flat connection like this, so we have seen that, okay, the topological Chern classes are trivial. So what next actually? So what else can you do? What kind of invariants you can attach? So now this is given by So how does one, in which cohomologies one would like to associate or construct classes? So for that, look at the universal coefficient sequence, Z to C mod Z, and look at the associated long exact sequence of homology groups. So now we have seen, is there a pointer? Pointer is not. Right. So you have this homology sequence, and so your integral Chern classes. So they are lying in this given degree homology with Z coefficients. And we have seen that once your vector bundle is equipped with a flat connection, you look at its image in 60 homologies, and there it is going to be trivial by Chern-wide theory. So essentially, it means that integral Chern classes. So essentially, so they are, so they have a pre-image in the previous degree homology. So there is some class in odd degree homology which gets mapped to your integral Chern class. But now that is not going to be an uniquely determined, right? Because there is something coming from the previous degree homology. So now, but at least it indicates that your integral Chern classes, so they themselves are not trivial, but they are torched because they are going to be zero in the next odd degree in the C homology. So essentially, at least it gives some idea that, okay, there are some classes in the odd degree homology H2I minus 1, which gets mapped to the integral Chern classes. So, but we just want to have some natural construction of such classes in the odd degree homology. So this is provided by Chern-Tiger-Simons theory. And what they do is that, so they introduce another homology theory, which is something which fits between the odd degree H2I minus 1 to H2I, something like this here. So there is some odd degree homology here, and that you can bring it out. So this is called the differential homology, another homology theory. So differential homology, actually, those were doing algebraic cycles and so on. So they are much familiar with Deligne homology. So Deligne homology is on complex manifolds, but differential homology, you can think of it as a real analog of Deligne homology because we are still working over smooth manifolds. So you can think of differential homology as real Deligne homology. Okay, so essentially their theory provides classes in the odd degree homology with C mod Z coefficients. And so this is with respect to your connection, with respect to any smooth connection. It need not be flat. You just start with a smooth connection. So you are able to define certain classes in this odd degree homology with C mod Z coefficient. Zi is actually the embedding of Z in sets. We just put that I 2 pi. Oh, because you have several embeddings of Z, you can attach them. Okay, so the differential homology, you can define it as a pair F comma alpha. So F is a cochain which is defined on your cycles K minus 1 cycles. See, because somewhere we want to say that we want some classes in your odd degree homology with C mod Z coefficient. So the way would be to look at F, which is defined as a cochain and whose boundary is actually form alpha here. And then whenever this alpha, the boundary is 0, so then that cochain descends to a co-cycle actually. So then you get a class in your odd degree homology. So that's how this differential homology is cooked up. And so one should try to identify this or understand differential homology via this exact sequence. It is saying that, okay, you have this odd degree homology which is in the kernel, And on the other part of this exact short exact sequence, so this is identified with the integral valued closed forms in degree 2i. Because somewhere actually your if you look at the classical Chern-Weil theory, your classes, so they are actually the form are in the smooth differential forms are in degree 2i, and they are closed, and they are also integral valued because you can also define them classically via the universal Chern classes. And so hence one should think of the differential characters lying somewhere in this middle cohomology group, and which gets mapped to something which lies in the other group. And whenever we know that such forms are trivial, so then they descend down to the odd degree cohomology, but with C mod Z coefficient. Okay, so this is how we can try to sort of understand differential cohomology. And so then again, the question is, how do you define the classes in a more natural way? And for this, actually, they essentially looked at the Narasimhan-Ramnan universal connection, because just as in the case of primary classes, so one looked at the universal vector bundle over a Grassmannian. So actually, Narasimhan-Ramnan also proved that such a universal vector bundle is equipped with a universal connection as well. And so one should first, if we want to define certain universal differential characters, so it essentially should mean that you should define universal differential characters on for a universal connection on a vector bundle over a Grassmannian. So this n capital N bracket little n. So this is a number which depends on the dimension of your underlying manifold you start. So in that situation, you look at such a universal connection, and on such a Grassmannian, so one can define the universal differential character. And this is essentially true because on a Grassmannian, there is no odd degree cohomology. So the universal differential character is precisely the lift of your Chern form. So what we have done, at least just try to remember that starting with a bundle with a connection on a Grassmannian, we are able to define universal differential character. So now again, as in the previous case, when we wanted to define the Chern classes, so you start with the vector bundle E together with a smooth connection nabla on a smooth manifold M. So then there is a classifying map F from your manifold to appropriate Grassmannian, where that capital N, little n depends on the dimension of your manifold M. So via this classifying map, you can pull back the differential characters, and you can define the differential characters on your underlying manifold M's. Okay, so just to summarize, so we have defined the classes associated to a vector bundle together with a smooth connection. So till now we haven't said anything about flatness, but let us now try to see about variation of flat connections. So variation of flat connections basically says that whenever you have a family of flat connections, say it is parameterized by interval, for example, a path, for example, and then you can just look at the difference of the differential characters of the connections, nabla 1 and nabla 0, which are the endpoints of your path, for example, and look at this difference. So this is precisely given by a odd degree form, this 2i minus 1 form. So this is called the eta form. And so at least we try to now analyze this formula carefully. So what this says here is that, so here at least just remember this I is different from this I. So this is square root minus 1, but the other one is, so there's some bad notation, shape perhaps. And okay, so nevertheless, what it says here is that whenever now your connection is flat, so that means your nabla square is trivial. So then the integrand is identically 0. So in that situation, what this means, this formula says is that the difference is 0. So that essentially says that your differential character is constant along a path. So this is a very useful fact because when we want to understand further properties of these invariants, so at least it says that we are going to look at the space of flat connections. So if you define the differential character at one point, it is going to be the same. It is going to be constant on that connected component of connections. So this is a very useful fact. And so this is also called as the rigidity formula. So whenever your connections, for each T, this is flat. So this is called the rigidity formula. And right. So let me just, so I've been saying about differential characters. So if you want to look at this map, so these classes are, see, whenever your nabla T is flat, so what one sees here is that the Chern form is identically trivial. So it essentially means that the differential character, which is in the middle, which is lying in the middle cohomology group, in that short exact sequence, it actually descends to the odd degree cohomology with C mod Z coefficients. So these are also called as the Chern-Simons-Chigger classes. And so here actually we require that I is at least 2, because in that situation it only we have that the integrand is identically trivial, because I is at least 2, so there are at least 2 terms to make that integrand trivial. So that's the only reason where I is required to be at least 2. Okay. So the next question is that now at least we have seen that this eta form is trivial. So is there some way one can lift those eta forms to give to provide classes in the previous degree cohomology, H to I minus 2 cohomology with C mod Z coefficients? And indeed, it's true that so there is this notion of integration along fibers. So this was, I think, looked earlier by Daniel Fried in physics. And so one can use his definitions and indeed obtain certain classes associated to a path of flat connections. One can associate an invariant in the cohomology degree 2i minus 2 with C mod Z coefficients. So this is something which had intrigued many people, like how do you lift invariants in the previous degree cohomologies further, and how one can do that. And so I have to say that this was some question raised by Konsevich. Wanted some Chow analog for this formula, for this form eta form. And then actually Simpson, he observed that actually this form eta should somehow give maps on the higher homotopy groups of the moduli space of flat connections. So to make their remarks precise, we look at we look at the moduli space of connections to start with, and then look at the simplicial set associated. Look at simplicial set which are defined by sequence of connections and so on. And indeed, one can make this lifting property more precise, so which we call as higher order liftings or higher order invariants associated to family of smooth connections or family of flat connections. And we do get the maps defined on the homology groups of the moduli space of flat connections, and which takes values in a direct sum of homology groups. So this is something, if you recall the rigidity formula, where we said that if you take a path of flat connections, then the differential character remains constant along that path. So it basically says that if you look at the connected components of your moduli space of flat connections, so on each connected component, you get only one, not one, but actually a bunch of invariants, which is in H. Actually, it should be direct sum of H2i minus 1. So for each I, at least 2, you get invariants associated to a connected component of your moduli space of flat connections. now actually, as we remarked earlier, that actually if you look at a path of connections, or more generally, if you look at a loop of connections, flat connections, so you would get some cohomology, not a single cohomology invariant, but again a bunch of cohomology invariants in the previous degree cohomology when k is 1, and then so on you can do it. So in particular, you would actually get homomorphisms defined on the homology groups of your moduli space of flat. Okay, so these are more formal constructions. I mean, the original construction is due to Chern-Giger-Simons, but one can just iterate it further and get certain maps like that. And but then the question is, how do you what is the nature of these maps actually? Like, what can one say further, in the sense that for special manifolds, for example, if your manifold is underlies a smooth projective structure, so then what can one say about the nature of these maps? Is it injective, bijective, and all kinds of questions one can ask. And for that, actually, we don't have any answers as yet. So at least look at start with the basic question. When you are just looking at the map defined on row 0. So this is on pi 0. So what this is here is that, okay, so if you look at certain nice smooth manifolds, so and if you look at this moduli space of flat connections, so we know that the pi 0, it has countably many components, and so that says that the image is again going to be a countable set. So in that sense, one can ask the question, rather Chern-Simons question asks that if the image is going to be a torsion subgroup, so torsion is precisely going to be something your invariance takes values in Q mod set, whenever I is at least. So this is the classical question. And so one can just extend that question to the higher order maps as well. And one can ask if the image of your maps defined on the higher homology groups, so they lie in the torsion subgroup. So, but as one can imagine, actually, even the classical question, we don't have complete answers. So one has complete answers when your X is a smooth, complex projective variety. And so that was proved by Resnico. And then when your X is a quasi-projective case variety, so we had some results with Simpson. And now actually we also want to look at the quasi-projective case in more detail. Yeah. Okay, so let me define these volume regulators. And so as we notice that your classical, the differential characters, so they lie in C mod Z, cohomology groups. So your C mod Z, you can write it as R mod Z plus I dot R. So your differential character, it can be split into two parts. So one is a real part, and then the other one is an imaginary part. So the imaginary part is what is called as the volume regulators, and the other part is also called as the R mod Z Chern-Simons classes. So actually, if one looks at the classical, not classical, but actually the original proof by Resnico. So to prove that your Chern-Simons classes with C mod Z coefficients, that is trivial, he actually proved earlier first that the volume regulators are 0, and then actually using that, he also again goes back to the universal situation, universal space where your which parameterizes flat connections, and there actually he observed that the volume regulators themselves generate the cohomology in odd degree of the universal space. So that is the classifying space of flat connections. So that is BGL with a discrete topology. And so that was his first observation. Just for him, it suffices to prove that the volume regulators themselves are trivial, and then he is able to prove that the R mod Z cohomology CS classes themselves are trivial. So now the next question which we look at is when X is a smooth projective variety and T is a normal processing divisor on X, and then look at its complement. And now you start with the flat connection on the open part too. Okay, so on the open set, you have a flat connection. So then there is construction due to the length. So where he considered, so there are several extensions of your flat connection over which extend across D. So, and there is one particular choice of that connecting that space of extensions, which is called as Berlin's canonical extension. And this is equipped with the logarithmic flat connection. So I don't want to really go into the details, I mean the definitions here, but at least I'll just in the next slide, I'll just give some idea what is Berlin's canonical extension looks like. And then we also assume that it has unipotent monodromy around the components of D. So at least for the moment, just assume that there is one special extension on the whole of X. So the first thing is that at least you have an extension as a vector bundle, so which we denote by E. And now at least whenever you have a vector bundle, it's an algebraic vector bundle, and so one can define the Chern classes of E. So the first thing is due to Eno, so where she made some computations on how to define the Chern classes of E with respect to the logarithmic flat connection, and she computed the Newton classes and so on. And she proved that the Chern classes of E themselves are torsion classes. So this is the first nice observation she made. It is, and so once we at least know that the Chern classes of the extended bundle are torsion, so then the next, so the what we can ask is that, okay, so your cohomology classes are trivial in the torsion essentially means that it is trivial in the complex cohomology. So that means it should come from classes in the odd degree cohomology classes with C mod Z coefficients. So is there some natural construction to construct the Chern-Simons classes for such a logarithmic connection? Remember that nabla here is not a flat connection, but it is logarithmic flat connection. So there needs to be some technology to define classes extended the Chern-Simons classes as well. And at least once the construction of these classes have been done, so then the next question would be to ask whether these extended classes are themselves torsion when your index is at least 2. So this extended classes. Remember that this question we are asking only when X is smooth and project. Okay, so now let us try to understand what is this canonical extension. So because anyway we are wanting to construct classes in the cohomology group, so that is a topological invariant. So we have to understand how this canonical extension looks, what information it gives topologically. So basically it corresponds on the open set, we know that it corresponds to a flat connection. So a flat connection basically comes from a representation of your fundamental group of your underlying space. So that in this case it is true. So that means it is a local system. And so then on the boundary, so you have several components here. And then for each component, look at some nice small tubular neighborhood of the divisor component. And there actually the extended connection, your logarithmic connection, because we assume that the monodromy is unipotent. So essentially it means that local monodromy, so it is nilpotent, and you can look at a nilpotent operator applied on your E restricted on the boundary. So you can you get a filtration, and on each consecutive filtered T's, graded T's, actually it is actually a flat connection. So essentially what we are saying here is that if you look at the associated graded, so then there is a local system on each of PG. Okay, so this is the topological data coming from canonical extension. So that's all we need to know to understand canonical extension, or rather to construct topological invariants from this data. So, but now actually as earlier, so when we want to construct topological invariants, so we again need to go to the smooth category and try to define a differential character which sort of encodes your original connection on the open set U, and then on each of these successive graded pieces, we have a flat connection, and then you have a. But why one is this is more tricky here is that because you are looking at several divisor components, and at the intersection there needs to be a common filtration, common splitting of your filtration, and that is not easy to achieve, and, but that is some theory and which one has to look at. So, but in principle, it is possible that whenever you have divisor components intersecting, and then you have a filtration coming from your connection on one component, and then you have another filtration coming from your logarithmic connection on that piece, and then there is a common filtration so that it splits, and then you can look at so once you have common filtration, I think there is some technology which Simpson knows, and he is an expert in that, and he is able to sort of handle that situation. Okay. So essentially, see, topologically, what one should do here is that you have, at least on the open set, you have your Chern-Simons classes. On each boundary component, you have a Chern-Simons classes, which also extend at least in some small boundary. And then you need to have some kind of gluing construction for all these classes. So topologically, the first idea would be to look at, say, a Mayer-Vittori sequence and try to see you can patch glue all these classes and get hold of a class here. But then one observes that that is not uniquely determined, but because there is something else coming from the previous degree cohomology. So again, one needs to construct a differential character. So for that, one needs a smooth patched connection, which such a patched connection should restrict to your original flat connection on U, and it should restrict to your what do you say, graded filtered local system, graded filtered connection on each of those PJs. So such a patch connection actually you can construct via partition of unity theory, and so this was something proposed by Delin, and one can construct a smooth patch connection which actually encodes the properties, the topological data which we mentioned earlier. So okay, so in this situation, when you are looking at logarithmic flat connection, so the curvature form is not zero. So because we want, when we want certain extended classes, we want that the Chern form should be trivial, and in the classical case, in the flat case, we said that the Chern forms are trivial, so the differential characters descend down to your odd degree homology. But in this situation, the Chern form is not zero, but now actually you just look at the trace forms of your curve. I mean, the Chern forms are zero because the trace forms, the curvature matrix is not zero, but the diagonal forms, the trace forms, so they are zero. That essentially corresponds to your Chern form. That becomes zero, and indeed the differential character descends to your odd degree homology. And this defines your extended Chern-Simons classes with CMOD.
Just a small point that you began with algebraic vector bundles, but at the end, the object that you invariant that you're getting of your topology. That's the case. But then there's some reason why, okay, to get hold of the data at the start, you need to begin with an algebraic vector bundle.
At least algebraic, or actually because we can to define this canonical extension to be the complex manifold equation of the part.
But the bundle also should be holomorphic.
Right, extended. So Delin's theory essentially says that the extended bundle is a holomorphic bundle together with the logarithm. But then what we are saying here is that your logarithmic flat connection is not good because because to define your extended classes. So if you replace this logarithmic connection by another connection, which is the flat patched connection, but which encodes the data given by logarithm. Okay, so that's this patch connection is not unique. There are several infinitely many choices for that, because at least locally we know that we are saying that on the open side you have a connection, a flat connection. On each boundary component you have a flat connection. Only that data needs to be encoded, and there are several choices for that. So, but it doesn't, because now we can use the rigidity formula and say that okay, whichever patch connection you choose, which encodes this data, the classes you obtain is uniquely. Okay, so this patch connection is not unique, but the classes they determine is uniquely determined. Okay, so that is this variational formula, and okay, so that's the point. So that's the construction of your extended Chern-Simons classes. And now again we want to understand the next question is how do you we again want to look at this question about triviality of the extended Chern-Simons classes themselves, because Resnico he proved it in the case of flat connection on a projective smooth variety, and now we just have a quasi-projective variety. You have flat, and then on the completed variety we also define extended classes, and we want to prove their triviality when I is at least 2. So, right. So recall how your volume regulators is defined. So, okay. So there is another way to look at define volume regulators, in the sense that we again go back to this formula which defines the rigidity of your extended classes. So this also we can put in this situation. And so what this says here is that now suppose if the endpoint, now suppose you start with your connection nabla, and nabla 0 is going to be trivial. So in that case, actually, you can define your Chern-Simons classes as precisely given by this integral. So now you look at the imaginary part of that. So that is a definition of your volume regulator. So you have sort of a precise, sort of a more so you can understand your volume regulator not abstractly, but by looking at this integral, and so that at least one can get some handle how to look at how to prove the triviality of volume regulators via this form. Okay. So now this proof is essentially due to Simpson, that indeed he proved that the volume regulators of the canonical extension are trivial. Okay. So this is when your boundary is a normal crossing device. So earlier actually we had this same result, but that time we had that the boundary was only a irreducible smooth device, and the whole variety is compact. But in this this is a more general case, and so what he says here is that he repeatedly applied the rigidity formula to reduce to the case when your connection is unitary, and observe that the volume regulators are trivial. And so now essentially he looked at the case when your local system you begin with is associated to a complex variation of Hodge structures. And so this is something again going back to Resnico's theorem, because if you look at the moduli space of flat connections on a smooth projective variety, and so there are special points in this moduli space, so they correspond to complex VHS. So in some sense, one can think of VHS as coming from the local systems, coming from family of smooth projective varieties. And in this situation, we proved that the connection actually is equipped with an indefinite Hermitian metric, so preserved by flat connection and so on. And so he did prove that in this situation of complex VHS and in the boundary, you have such nice situation that the volume regulators are trivial. And then again, the step 3 says that look at the variational formula or the rigidity of volume regulators, and to conclude the triviality of volume regulators for canonical extension. So now the next question is, what about the R mod Z Chern-Simons classes? And because if one looks at Resnico's original theorem, So he had a universal the classifying space for flat connections. So this is some BGL with the discrete topology. And there actually, in this universal space, actually he proved that the Chern's R mod Z classes tensors are true using some theorem of Torus. But now, if you look at this extended canonical extended classes and the canonical extensions, so there is no such universal classifying space. So what one can do next is to construct that he constructed certain cubical complex, which is sort of a classifying space for canonical extensions and cubical space, and then he defines. I think this part is not complete yet. So at least here we know that the volume regulators are trivial, and but then there is a good chance that R mod Z cohomology, or rather the odd degree cohomology, with this cubical space tensors are trivial to conclude R mod Z. Okay, so this is something very technical. So stop here. Do I have time?
Yeah.
Fine. Okay, so this is the part, and so just to give some motivation, why one's interested to look at all these questions about triviality and so on. So this originally came from law of nature. Okay, this is that we start with X assessment for regularity. There were complex numbers. And in this equation, we started with the multiplied vector connection. And this equation, so what we said was that one can still define Chern classes of E. So it doesn't consider it doesn't say anything about the connection. That is, the Chern classes are defined with tau groups. Projective connection and this tau groups with two conditions, rational conditions. And so there is another connection. Maybe say that the tau groups are equal. Filtration, a finite filtration. So that I plus first E trivial. What one knows here is that the first part, the first filtered piece, can take this to be now of X. And the cycles, the homology. And the next piece is taken in certain table to X, two quantities. So it's the cycle plus which take values one from one to X. And the first filter is going to be the kernel of this. So it is kernel of this cycle plus. And I'm able to go to that. So we define the kernel. So now compact complex torus. And then you look at the kernel of it. So that is precisely taken into of the since now the proposed interpretation to understand the structure of these downwards. And so we also said that I could also have other component properties and so on, which is our equation. And so also that it's not a never-ending configuration, but that's just solve at the equals first stage. So okay, so coming to this flat button with the connection, flat connection. So what the proposed was that turn classes actually should lie in the lowest trigger. So if you look at MI, so I turn class like this. In fact, it should lie in the deepest level of the trigger. But since the I doesn't know the trigger is beyond S2, it also written as PI of E. Actually, I know that I is at least. Which is like MI, but the varying commodity is something of course intermediate commodity that is that will have to be intermediate. So that's what it is. So that is varying commodity. So this is our house. And so one it also said that if the link is related is actually related to the question because or if the common more central, so it actually gets not very important. And the classes defines that. So this is another thing one has to do that one too, because all the perceptions of one excellent classes here and rational. So one should actually try to go that classes on that to be so much very so that is it should be some maybe that one is falling very some so to that a family of varieties. So on this now suppose P was actually projected, it's very there. And to find projective base, suppose but actually so in that case actually I find then from this original equation where connection and so that the classes of finals. So these are actually the complex technology model with a platform something. So in this situation when I equals to 1. So 1 plus just know that if I'm going to write it down. Here is actually one is looking at the family of straight complex family of the given and so now we are going that place. And now supposedly there's a nice good compact equation so that the complement is on top of the other. So okay, so in that situation, so this is the reason why I was presenting the canonical extension. But one reason that the base almost never projected and that family of transform variety. And so you need to look at consider each element. But the vector bundles they don't extend as black variety, but as cases, but they come with extra structure. So you can look at exception. Okay. So you can ask me questions on this last part. Rushed up.
Anybody online?
Go to the lowest dimension in which this blocks conjecture is difficult to covers everything that surface and the first already it's open.
No, that is done. Progressing family of surfaces. So that basically called family of surfaces.
What is this divisor or divisor maybe
First, let's say, one is
Further comments, let's thank the speaker again. There were some announcements.
Yeah, actually, I wanted to say something about the faculty and information of our university. So the Wi-Fi connection is some of our testing problem. They are not able to connect the device. We will fix that thing as soon as possible. I think the canteen location, I think we have student only one mess currently running. So you have passport of that student mess. Breakfast, lunch, dinner will be there. And breakfast time, there is a, I think, it's 8 o'clock, 9 o'clock. Breakfast time and lunch. Today's lunch will be 1 to 2:30. And next onward, 12:30 to 2 o'clock lunch time. And dinner 7:30 to 9 o'clock. And those who are staying in hotel for them breakfast and dinner already arranged. And for those who want to have, we have two small cabin areas. One is in this building, third floor. If you want to have payment with 15 rupees per car, you can have. And the next to Ganga Hostel one, we have one more cabin. It's a very small one, and it will open 9 o'clock to 8 p.m. And bus time today we had that communication with the bus driver. We are sorry for that. So it is that bus will start to 5 minutes past 8 o'clock. And so today to late, but tomorrow onward I think it will go. And campus to Lemon Tree Hotel by 5:45 p.m. just in front of our campus. And the discussion room, we have two discussion rooms. Suppose we want to discuss at the same floor, that side of room number is 501 and 5. You want to have discussed. And as to your reimbursement form, so please some of our organization you can submit the form or whatever the documents you have. Me, Sanjana, and Shura. So and our officers, our colleagues are arranging this. Okay. Okay, then now we have coffee time.
Yeah, so our next speaker is Professor Sudarshan Kuchar from IIT Mumbai, and he'll speak on Zariski's finiteness theorem and properties of some rings of invariance.
Yeah, thanks a lot. Do I need to use any stand up?
That's the first time we stand up.
Okay.
Column method.
And capture it in your world.
Here we only would speak.
Oh, yeah. 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 So let me, like all the other speakers, begin by thanking the organizers for organizing such a wonderful conference. The arrangements have been excellent. And thank you for the invitation. So the title of the talk is Zariski's finiteness theorem and properties of some ring of invariants. Moving ahead. Okay, so it's really a two-part talk. The first is on the so-called Zariski's finiteness theorem. Come to what that is, and the second is about some properties of the ring of invariance under GA actions. GA for field K is the field K with respect to addition, and everything that I say is joint work with another Gurjar and our joint student Buddhadev Hazara, part of his thesis. Okay, so let me begin by recalling the famous Hilbert's 14th problem. So begin with the field little k and let capital K be the subfield of the field of rational functions in one variable, namely little k round bracket x1, x2 to xn. Then is k intersection the polynomial ring little k x1, x2 to xn finitely generated over k? This is a question Hilbert raised here 1900. Subfield of this field k x1, x2 to xn is capital K. Take k intersection the polynomial ring in n variables over little k. Is that finitely generated over? And this was settled affirmatively by Zariski for n less than or equal to 2. And Nagata gave a counterexample to the Hilbert problem in general in 1958. And Zariski generalized this problem as follows, in a very natural way actually. Let T be a affine normal domain over K with quotient field L. Suppose capital K is a subfield of L containing little k, then is T intersection K finitely generated over K. So the polynomial ring essentially being replaced by any affine normal domain. Sorry again. Affine normal domain. Affine normal domain by which I mean finitely generated algebra over field. Yeah. Yeah. So T is always finitely generated K algebra. And in 1954, Zariski settled the Zariski finiteness conjecture in the case where transcendence degree of capital K over small k is less than or equal to 2. And in 1958, David Rees came up with this counterexample to the Zariski's generalization of the Hilbert's 14th problem in the case where the transcendence degree of capital K over small k is equal to 3. But this example didn't work as a counterexample to Hilbert's 14th problem itself. And then finally, the same year, after the appearance of David Rees's counterexample, Nagata produced the first counterexample to Hilbert's 14th problem. This counterexample was in the case where the transcendence degree of capital K over small k is 13. So that is now this is theorem. Let me restating it. T is a affine normal domain over K with quotient field L. Capital K is a subfield of L containing K with transcendence degree of capital K over K less than or equal to 2. Then T intersection K is finitely generated over K. This is the Zariski's finiteness theorem. And Zariski's proof is non-trivial when the transcendence degree of capital K over small k is equal to 2, and probably not so well known. Yeah. I don't know. Answer is I don't know really. Probably not, but I would think that this is harder. Okay, so now come to some power work. We gave a new proof of an important special case of Zariski's conjecture. And the proof is a combination of commutative algebra, algebraic geometry, and algebraic topology. The novelty feature really being to introduce some algebraic topology in the whole game. Hence, whenever the arguments are topological in nature, we assume that K is the field of complex numbers. So theorem 1, let T be an affine normal domain over K with quotient field L. Suppose little k contained in capital K contained in L is an inclusion of fields where capital K is a field of transcendence degree 1 over K, then S equal to T intersection K is finitely generated as a K algebra. So pretty much the same as before. So this is the first theorem for which we give an alternate proof. And the theorem 2 is a little different. Let T be an affine factorial domain over K, and let S be an inert subring of T, so that the transcendence degree of S over K is equal to 2. Then S is finitely generated over T. S is similar to the one in the S is same as T. Yeah, but that in some sense, okay, more assumption. Inertness is a yeah, that's the next slide. So subring A of an integral domain B is said to be inert in B if given non-zero elements A and B in the bigger ring. The condition AB belongs to the smaller ring implies that A and B both belong to the smaller ring. Now an element is so how do these examples arise? Well, one way in which such examples arise, important examples of inert subrings come from the ring of invariance of a GA action or a connected semisimple group on the polynomial ring over a field. The key point about both these, whether it's a GA or connected semisimple group, is that there are no characters. That is crucial to inertness. I think it's okay even if it's a unipotent group, probably. This is what inert is. Just pause for a few seconds at the end of every slide because these talks can go a little fast otherwise. 2 years of online teaching has taught us that. So we repeatedly used a special case of Zariski's main theorem, namely that a quasi-finite birational map of normal varieties is an open immersion. Any quasi-finite birational map of normal varieties is actually an open immersion. So Zariski's main theorem, maybe not Zariski's, maybe the original form in which Zariski proved his theorem, perhaps. We also use the following lemma crucially. The lemma: let R1 contained in R2 contained in R3 ... be affine normal domains defined over an uncountable field K contained in an affine domain S. If each of the maps spec Ri plus 1 to spec Ri is quasi-finite, then the above sequence stabilizes after a finite state.
Again, finitely generated.
Yeah. I assume. Yeah. The affine domain, when I say it's always finitely generated or the ground. So increasing sequence of affine normal domains or uncountable field, all of which are contained in an affine domain S. If each of the induced maps is quasi-finite, then the sequence stabilizes after a finite state. Okay, so this is rather nice. Let me just quickly give a proof. So suppose some extent the idea that going to the proof will be used later. So let Vi equal to spec of Ri, and the inclusions Ri inside Ri plus 1 induce dominant morphisms from Vi plus 1 to Vi. Furthermore, we can assume that all the Ri's have the same quotient field. Eventually, all the Ri's will have the same quotient. So you can begin. I'm sorry.
Only finite action, not birational.
No, not yet. But eventually, because of the union of the quotient fields of Ri will be something finitely generated. At the level of quotient field, when you take the union, it's contained inside the quotient field of S. Therefore, it's going to be, therefore the union of the quotient field is finitely generated over K. So eventually, it will pick up all the generators.
Contained in domain S.
Contained in the domain S. Yes. There is some boundary thing. So we can assume that all Ri's have the same quotient field. So, the next line says it, in fact. So this is because union of quotient field of Ri is finitely generated over K, since it is contained in the quotient field of S and S is affine. So hence, without loss of generality, we can assume that all the Ri's have the same function field, the same quotient field. Hence, by Zariski's main theorem, the induced morphisms Vi plus 1 to Vi are open immersions. So suppose the chain does not terminate, then the higher Vi's will be obtained from the lower ones by removing more and more divisors. No. No, otherwise it may not be divisors. No, indeed. But I'm saying even if you remove divisor, it may not be affine. Something affine, if you remove divisor, it may not be affine. It's true only in dimension 1 and 2. Yeah. So suppose the chain does not, then the Vi's, the higher Vi's are obtained from the lower ones by removing more and more divisors. But V1 is dominated by spec S, and hence its image is constructible and contains a non-empty open set. This open set is common to all the Vi's, and therefore the chain terminates at a finite stage. So you are removed more and more divisor, you are getting smaller and smaller open sets. But the image of spec S inside the first one is already some open set, contains an open set. That open set has to be common to all of them. So you cannot have ever decreasing sequence of open sets. So therefore the chain stabilizes. So this is easy algebraic geometry for. We now apply this to the first of the two theorems stated earlier. Namely, I'm just restating exactly the same theorem as before. Affine normal domain quotient field is a subfield of L with transcendence degree 1, then S intersection T, T intersection K is finitely generated as a K algebra. Proof. So since T is normal, S is also normal. And since S is a countably infinite dimensional K vector space, we can find affine domains R1 contained in R2 contained in R3, etc. with quotient field equal to the quotient field of S and whose union is equal to S. So write S as an increasing union of affine domains, each having the same quotient field as S. So we will prove that for some sufficiently large I, S is equal to Ri. That would prove finite generation. So let Vi be equal to spec of Ri and let W be equal to spec of T. So there are dominant morphisms phi I from W to Vi induced from the inclusions Ri inside T and Fi from Vi plus 1 to Vi induced from the inclusions Ri inside Ri plus 1 for all I with the obvious commutativity diagram. W maps to Vi plus 1, Vi plus 1 maps to Vi, and there is a commutativity diagram. So I'm sorry, I should be close to this, I think. Right? Is that? Oh, yeah.
It's very fine.
Okay. But I can't. It's a little uncomfortable. Right. Now, since VIs are all curves, notice that I'm assuming that the transcendence degree is 1 now. So since VIs are all curves, the maps Vi plus 1 to Vi are quasi-finite. Non-constant map between irreducible curves, so that's quasi-finite. And since each Ri is contained in T and T is normal, by the earlier stated lemma, the above sequence of Ri's stabilizes after a finite step, and this completes the proof. We proved earlier in the previous lemma that you have an increasing sequence of normal affine domains over a uncountable field. If the induced maps are quasi-finite, then the sequence stabilizes. So this is the immediate consequence of the previous lemma, therefore. Yeah. Yeah, when you are not really working with algebraically closed fields, I mean, the statement that I made about the image being a constructible open set, etc. That's where I mean, maybe it can work more generally. I'm not. Yeah, exactly. Some kind of bare category theory argument. When you remove countably many divisors, the complex of all of them can be empty. That kind of thing can happen. Some kind of bare category. Yeah, possibly. Yeah. Okay. Now the proof of so this was theorem 1. In the case where capital K has a transcendence degree 1 over little k, the theorem 2 is about the inert subrings of yeah. You have an inert subring of a factorial affine domain with transcendence so that the transcendence degree of S over K is 2, and you want to prove S is finitely derived. So this is the second theorem. Stronger assumption than in theorem 1. Okay. So the proof of theorem 2 is substantially more complicated and uses standard topology, uses a fair bit of commutative algebra, and also uses topology. Theorem 2 is more complex. Yeah, that's what that is more complex numbers. That's what I said right at the start. Wherever we are using complex topological arguments, implicitly field will be complex number. Yeah. So lemma, let V and W be normal irreducible algebraic varieties, and let F from W to V be a dominant morphism. Then the first Betti number of W is bigger than or equal to the first Betti number of V. Normal irreducible algebraic varieties, and the first Betti number of the domain dominates the. And the second is begin with a complete algebraic variety of dimension D over K. Let D1, D2, etc. be a sequence of distinct irreducible divisors in Z. Then the first Betti number of you remove the first of all you remove the singular locus, and then you remove more and more divisors DIs. Then the first Betti number tends to infinity. Begin with some algebraic variety of dimension D, and we remove more and more divisors. The first Betti number is also goes to infinity. Something consistent with our intuition. Remove something of 4 dimension 1, something of real 4 dimension 2, then the. So the proof is a consequence of a resolution of singularities and long exact homology sequence for pairs. So I'll omit this proof. So we'll now come to theorem 2, which I'll restate. Yeah, this is what I want to discuss. Affine non-factorial domain. This is an inert summary, and this is finitely. So sketch of proof. Let W be equal to spec T. The first step is to construct an affine normal domain R1 with R1 contained inside S, so that the quotient field of R1 is the same as quotient field of S. Something we have seen before. And note that therefore dimension of R1 is necessarily 2. Transcendence degree is 2. So this dimension of any affine domain is equal to transcendence degree of its quotient field. So this dimension is equal to 2. Now one can further assume by enlarging R1 inside S, if necessary, that the morphism W to spec R1 has the property that the fiber over any point has codimension at least 2. And this part is non-trivial and is the hardest part of the proof. And it uses the inertness of S in T. So by enlarging S, but enlarging it within, by enlarging R1, but enlarging it within S, one can ensure that the map from W to spec R1 has the property that fiber over a point does not contain any divisors, 4-dimension 2. In some sense, this is where all the hard work goes in. exactly what I will not discuss in detail. So
You use implementing devices thrown away and the rest. Even strictly increases.
no, that comes later. At this point, it's just pure commutative algebra. One has to use both the things, factoriality of T and inertness of S. Both of them are used in getting to this point.
Because they are saying it's quantified.
No.
W is also dimension.
No, W is higher dimension. Spec, W is spec T. T is something could have any arbitrary higher. Yeah. So now if R1 is not equal to S, we can find a bigger subring R1 contained inside R2 contained inside S with the same property and so on. So since S is countably infinite dimensional vector space, we can find a chain of affine normal subrings R1 contained in R2, R1 strictly contained in R2, strictly contained in R3 and so on, all contained in S, all having the same, I use the word function field, depicting geometry in my mind. I say same quotient field as S, and with the property that the fiber of the natural map from W to spec Ri has the property that fiber over any point has codimension at least 2. So one S can be written as an increasing union of such affine domains, so that affine normal domains, the W to spec Ri fiber of anything, any point has codimension 2 or more. Now it's time to use some topology. Look at the induced map on the associated varieties. Now, by taking suitable open subsets of Vi, say Vi prime inside Vi, obtained by removing divisors in Vi, and with image of Vi plus 1 prime contained inside Vi prime, we construct a sequence of morphisms V1 prime, Vi plus 1 prime mapping to Vi prime to Vi minus 1 prime and so on, so that each of these morphisms is quasi-finite. So the originally, if you look at these inclusions, R1 contained in R2 contained, etc., the map at the level of varieties may not be quasi-finite. Certain curves could get contracted to points. So here, so far, at this point, the maps are not quasi-finite. But now, by looking at these Vi aspect of Ris, by throwing suitably many divisors and throwing them in some compatible fashion, one can ensure that you have open subsets Vi prime inside Vi and maps from Vi plus 1 prime to Vi prime, such that these maps are now quasi-finite. And such that the global sections of V1 prime is contained inside global sections of V2 prime, ... contained inside S, contained inside T. And union of global sections of Vi prime is equal to S. So global sections of Vi prime, I have not given it a name, let's call it Ri prime. So you have Ri contained inside. So Vi prime contains is an open subset of Vi. So Ri is smaller than Ri prime. So since union of Ri is equal to S, union of Ri prime is also equal to S. So it takes it's not difficult to construct these Vi primes. Can be constructed in some, think a little bit. These can be constructed. Basically, every time you have curves contracting to a point, you throw away those curves, throw away all their inverse images, and get quasi-finite maps. This uses Hartogs theorem and the inertness of S in T. Yeah, I should say this still uses some commutative algebra. It's not pure topology. It uses inertness of S in T. Now, global sections of Vi prime are all finitely generated by theorem of Nagata. From an affine domain of dimension 2, to remove divisors, the complement is still affine. It falls in dimension 3 and more. So, therefore, the global sections of Vi prime are still finitely generated. and the morphisms vi plus 1, vi plus 1 prime to vi are now quasi-finite and birational, and hence by Zariski's main theorem, they are open emergence. And now, as before, the higher vi primes are obtained from the lower ones by removing more and more divisors, and therefore the first Betti number of vi prime tends to infinity with I. That was the earlier proposition I stated. But first Betti number of v1 prime is bounded above by that of first Betti number of w, which was spec t. Everything was contained inside t. So first Betti number of vi prime is bounded above by that of spec v1. This is a contradiction, and it shows that the above chain terminates at a finite stage, thereby proving finite generation.
But you could use the lemma to have a infinite concept of quasi-finite math. At the same function.
No, you see, there's a small problem. All the VIs are contained inside T. Not VI, RIs are contained inside T, but these RI primes are not. So they are not contained inside T. Nevertheless, the Betti number argument still works. The Betti number is still bounded by the Betti number of W. Right, primes are not by inverting. RI primes are obtained by removing some divisors, so it's bigger. Okay, so this completes the and the immediate corollary therefore is you take a affine factorial domain over K, assume that G is either unipotent or a connected semisimple group defined over K. Let G act on T regularly so that the transcendence degree of the ring of invariance is at most 2, then the ring of invariance is finitely generated over K. This is because, as I remarked earlier, when you have a action of unipotent or a connected semisimple group, the ring of invariance is an inert subring. And so immediately the immediate consequence of the Zariski finiteness there. No, it's known before, but the difficult proof of Zariski and entirely algebraic. As I said, the main novelty is to use invoke topology here. So proof this follows immediately from the above theorem after invoking the fact that G has an hypothesis. The TG is an inert subring on. Okay. Time. How much time left? I completely forgot when I started. 12. Okay. What about you? Okay, now comes the second part of the talk. Is about G actions on affine domains. So as a warm-up, let me recall the following well-known results. So this is Weizenbach's theorem. If the additive group GA acts on the polynomial ring linearly by K algebra automorphisms, then the ring of invariance is finitely generated. Famous Weizenbach's theorem. Sexuality gave an alternate proof. Sexuality's earliest papers. Now let R, so let R be a regular affine domain of dimension 1 over C, and let C equal to spec R with the corresponding smooth affine curve. Let GA act by R algebra automorphisms on the polynomial ring R x y z, and let S be the ring of invariance. Then it's a theorem due to Bartodecker and Daniel Degle that S is finitely generated over R. So with this background, our aim was to prove the following theorem. So let R be a regular affine domain of dimension 1 over C.
Actions on polynomial. So if I take it here, it should be an embedding, right? There's only one place I think.
Go back one, like.
No. Action 24 is there or embedded.
Some of stabilizers cannot be all of G, you say?
No, all of G, yeah, can be.
Yeah.
That can be a fixed point.
Yeah. Yeah, otherwise it has no subgroup.
That's right.
Yeah. Okay, so with our aim was to prove the following theorem. So let R be a regular affine domain of dimension 1 over C. Let T be a uniformizing parameter of on R at the point P0 in C equal to spec R. Let GA act by R algebra automorphisms on R, X, Y, Z, and let S be the ring of invariants. Suppose F0, which is spec of S mod TS, is normal, then F0 is isomorphic to A2, and spec S is a trivial A2 bundle over spec R in a neighborhood of P0. So one is looking at you have this curve C. One is looking at A3 over this curve C. GA is acting on it, fixing the curve, and you are taking quotient by GA. That quotient, whatever it is, has a morphism to the base curve C, and sort of if you look at one of the fibers and suppose the fiber is normal, then it is actually has no singularity, it is actually smooth. So basically what happens is when you take quotient modulo GA, the general fiber is going to be just A2. There may be some bad fibers, but if the bad fibers are normal, then they are not bad. They are actually A2. Sorry? No, I'm saying to take A3 over this curve C, to take the GA quotient by GA, the quotient A3 over the upper, the relative A3 over the curve C, and take the GA quotient. That quotient has a map to the base curve because the GA is acting by R algebra automorphisms. So you take the structure morphism from the quotient to the base curve, take the fibers. The generic fiber will be A2, I'll come to that. And the special fiber, if it is normal, it is actually smooth and it's A2. So Daniel Degle and Julian Freudenberg, they have given examples to show that F0 can be non-normal. Assumption is not taking under if you drop the assumption C or the word. No. In some sense, we are assuming. Assuming that this is normal, then it is A2. So it may not. Assumption is not empty. Not vacuous one. So let capital K be the quotient field of R. R is the coordinate ring of the base curve. I sort of think geometrically, so I've written something more algebraically, say it more geometrically. Let transcendence degree of capital K over C be 1. Now, by a result of Miyanishi and Kambayashi, if I take capital K X Y Z GA, this ring of invariance is actually K U1 U2 for some suitable algebraically independent elements U1 U2 in K X Y Z. So K X Y Z GA action is again polynomial ring in two variables. This has the implication that if I take this morphism from spec S to C, S was the ring of invariance. If I look at this morphism from spec S to C, this has generic fiber A2, and hence the general fiber is also A2. That's the immediate consequence of the theorem of Miyanishi and Kambayashi. The aim then is to prove that this special fiber F0 is A2.
General fiber must also follow the previous one. Because every fiber is not normal with the total stage of normal. Because your general fiber is normal, so it's already 8.
He's trying to prove the previous. Well, I'm trying to prove the theorem. So, then, okay, so the aim then is to prove that the special fiber is also A2. Then by a well-known theorem of Sake, it follows that this fibration is an A2 bundle Zariski local. So if you have a base curve, your fibration, all fibers are A2, then it's actually an A2 bundle Zariski local. That was the non-trivial theorem of Sake. So towards this end, one first shows that this F0 carries a GA action. This part is easy. Especially. Okay, won't go into that. Therefore, it admits an A1 fibration from F0 to T for some smooth affine curve T. Now, by a result of Miyanishi, F0 has at first cyclic quotient singularities. This means that at a singular point of F0, analytically, locally, the space looks like C2 mod of finite group, where the action of the finite group fixes the origin and is free outside it. So analytic locally, it is C2 mod of finite group. That's how the singularities look. In fact, the singularities are rational double points. This means that when you take a resolution of singularities, you have a chain of P1s and every component has self-intersection -2. And that's what rational double point is. Okay, so one has this F0 and it carries a G action. This G action has nothing to do with the G action one started with. That was a G action on a certain threefold, not threefold, relative threefold. And now one is taking the singular fiber. This singular fiber comes equipped with a certain G action. One can show that G action has nothing to do with the original G action one started with. And therefore, the usual G action implying A1 fibration. So there is a A1 fibration on F0 with smooth affine base curve, and the singularities are at worst cyclic quotient singularities. Now making heavy use of standard algebraic topology, homology with compact support, Mayer-Vittori sequence, universal coefficient theorem, Poincare duality, etc. All these have to be used and used repeatedly, so to say. We proved that F0 is a Z homology plane. That means all the homology group with Z coefficients are 0. So how do you get this reaction on F0? That sort of, locally, you think of, you have this F0. Look at the punctured neighborhood across A2. On that, there is a G action. You can see that it extends to this fiber. So outside, nearby, all the fibers are A2. So there is this G action, and the base is, let's say, like a Euclidean disk. So it's like a punctured disk across A2. Outside that, on that there is a G action which one can show extends to F0. One singular fiber. No, I mean the theorem is local. F0 is one singular fiber. One singular fiber. And in terms of the result is also local. One is proving that if this fiber is normal, then it's locally around that it's a A2 bundle. So if they are more than the same thing, same thing. So F0 is a Z homology plane. So all homology groups are 0. Now by the surjectivity of the map from F. So when I stated that the first Betti number of the domain dominates the first Betti number of the base. So the map from the first homology of F0 to first homology of T, this is surjective. But F0 being a Z homology plane, that first bit homology is 0. So the first homology of the base curve is also 0. But the only smooth affine curve with vanishing first homology is the affine line. So therefore, the base of this morphism is A1. Now one knows that the singular fibers of such an A1 fibration are disjoint union of A1s, possibly with multiplicity. Okay. But now if you compute the Euler characteristic, you can easily see that if there are more than one components in the singular fiber, then the Euler characteristic will be greater than 1. On the other hand, being a Z homology plane, its Euler characteristic is 1. So the singular fiber of this A1 fibration on F naught has the property that it is the singular fiber is irreducible, and therefore it's an A1, but could be a non-reduced A1. The A1 could have multiplicity, but it's irreducible. Okay. So all the fibers of the A1 fibration on F naught are irreducible and isomorphic to A1 when taken with reduced structure. Now again, using some standard algebraic topology, we show that for a singular point P on F naught, the first homology group of a small punctured neighborhood of the singular point is 0. Okay. But now, since the singularities on F naught are cyclic quotient singularities, by the famous theorem of Mumford, it follows that the point is smooth, because it's a cyclic quotient singularity on the one hand, and therefore, if one proves that the first homology of the punctured neighborhood is 0, that also tells you that the local fundamental group at that point is 0. But local fundamental group is 0 implies that the point is smooth. Is the famous Mumford's paper. So therefore, F naught is actually smooth. So combining all this, it follows that F naught is non-singular, and the base and all the fibers of the A1 fibration are all A1 with reduced structure. Now, using the ramified covering trick, it follows that the fibers are actually A1 even scheme theoretically. So that last part, one can take a ramified cover of the base, take the pullback, and take the normalization, and make an argument to show that Fourier. I mean, basically, what will happen is if some fiber has multiplicity, then by taking a suitable cyclic, suitable ramified cover of the base and taking normalized fiber product. So the normalized fiber product will give an étal abelian cover of the given variety. But the first homology group is 0, so there are no étal abelian covers. So that shows us that all the fibers had to be reduced to begin. So from this, it's easy to see. So now we are everything is done in some sense. The base is A1, all the fibers are A1 even scheme theoretically. From that, it follows easily that F naught is actually A2. And I think I have run out of time now. Yes, please. 7 minutes. Okay. So combining all this, we find that F naught is A2. So this completes the proof theorem. Let me just go back to the theorem for half a minute to see what we have proved at the end. So R is the affine normal domain over dimension 1. Is the uniformizing parameter. GA acts by R algebra automorphism to R x y z S with the ring of invariants. Suppose one of the fibers, the spec of S mod PS is the fiber over some point, over the point P naught in this case. Suppose that is normal, then it is isomorphic to A2, and spec S is a trivial A2 bundle over spec R in a neighborhood of P. This one. Sometimes after a long proof, one forgets what one has proved. It's good to come back to the theorem. That is Satte's theorem. Once you prove that it is A2, once you know all the fibers are A2, so what you proved is all normal fibers are A2. Yeah. There is a non-normal case. Yeah, and they do exist. So one can't do anything in some sense. Okay. So another theorem we proved was in some sense a slightly stronger version of Fick's result. If G acts regularly on affine space AN, so that the quotient AN mod GA exists as an affine variety, assume that the image of the quotient morphism AN to AN mod GA contains the singular locus of AN mod GA, then AN mod GA is Gorenstein with rational singularities. In particular, AN mod GA has canonical singularities. And Andreas Fick had proved that AN mod GA is Gorenstein, assuming the action of GA on AN is linear, but without assuming surjectivity of the quotient norms. The proof is obtained by combining the works of many authors. I also confess that I don't understand all the inputs that go into the proof. So it's combining the work of many people, and I haven't sort of gone through those references in any detail. So it's really an easy proof, but easy after combining many works. But so yeah, so you have G acting on AN, take the quotient morphism. If the singular locus is in the image, then the quotient is Gorenstein with rational singularities in particular there. Now, immediate consequence of this theorem. First of all, there are examples of G actions on A4 for which the quotient morphism is not surjective. There are such examples, so this hypothesis cannot be dropped. Now, corollary, let GA act regularly and linearly on AN. Assume that AN mod GA has an isolated singularity at the vertex. Then AN mod GA has a Gorenstein canonical singular point at its vertex. Proved by Weizenbach's theorem, AN mod GA exists as an affine variety. Since the action of GA is linear, the ring of invariance is positively graded. Now, clearly, the vertex of B is in the image of the origin in AN. So that's the only singular point. That's what we are assuming. It's an isolated singular point at the vertex. Now the result follows from using the previous theorem. If the singularities are in the image of AN contains the singularities, then AN mod G is Gorenstein with rational singularities. So that follows because we know that AN mod G looks like a cone. And at the sort of peak, you have a singularity which is in the image. So previous theorem tells you. The link to the paper.
Further questions or comments? Sure. Let's start this later again.
Already the place and so last time and we will be reviewing
Just follow.
okay, this button so just follow. Lunch.